Now that we have experience working with lump sum payments and compound interest, we're going to extend the idea out to looking at future values with regular payments. So whether that's an investment that you're making a regular payment into your retirement account, or a home loan or a car loan that you're working on paying off with regular payments. That's what we're going to take a look at today. Today we're going to solve problems with annuities An annuity is an investment that you're making regular payments into, like 10% of your check goes into retirement every time. With annuities and loans. And so we're going to start with the annuities. And let's just define it formally. You're making regular payments into an account that is earning interest at the end of the period. And the equation we use for these annuities is a little more involved. Actually, there's only one, so let's not make it plural. The equation we use for the annuity is A, the future value accumulated amount is equal to the regular payment times, and we're going to have two parentheses. That's going to be important when we get to the calculator. 1 plus r over n to the nt minus 1 all over the rate divided by n. And we've seen most of these variables before. We'll just redefine them all formally. A is the accumulated future value. R we've seen before is the interest rate. T we've seen before, that's the time. And as usual, it's always in years. N we've seen before, that's the number of compounds. It's also going to match the number of payments per year. So if you're making quarterly payments into the account, it's going to be 4. If you're making monthly payments into the account, it's going to be 12. If you're making semi-annual payments into the account, it's going to be 2. The only real new variable here is M, and that's the regular payment. And we use M because most often we're talking about monthly payments. So much going into accounts every month. So this is the big equation for today. Technically there's 2 more, but this is really the one that we're going to use to drive the other ones. So let's try some accounts with some annuities and see if we can solve them. So let's say $200 is deposited each quarter into an account paying 9% for 5 years. And we're going to look at how much money this comes out to be. And we get this off of our future value because it's paid each quarter. Our future value of an annuity is equal to that monthly payment times, with 2 parentheses, 1 plus r over n to the nt minus 1, close the second parentheses, all divided by r over n. So $200, that's the periodic payment. That's our M. 9%, that's our interest rate, 0.09. The time is 5 years. And those payments are made quarterly, so the number of compounds, the number of payments is going to be 4, paid quarterly. So taking the information in this problem and plugging it into our equation, we have A equals the periodic payment of 200 times, with 2 parentheses, 1 plus 0.09 divided by 4, all to the nt, which is 4 times 5 minus 1, close the parentheses, all over r over n, which is 0.09 divided by 4. So to get our final answer, we just have to plug this into our calculator. The catch is we want to make sure we plug it into our calculator correctly. A couple things to help us as we plug it into our calculator. Some calculators require parentheses around the exponent if there's stuff going on up there, which there is. Some don't require it, but it doesn't hurt to put it in. All calculators, though, are going to want you to put the denominator in parentheses. Otherwise, it's going to mess up the order of the division and the multiplication. So you need to remember on the calculator, we have an extra set of parentheses for the exponent and an extra set of parentheses for the denominator to make sure the calculator interprets it correctly. So let's plug this into our calculator and see what we end up with. I'm going to move my calculator down a bit here so that we can see it better. There. You want to see the whole calculator, right? All right. So we've got 200. Then we need the 2 parentheses. So we're going to hit the parentheses button twice. 1 plus 0.09 over 4, close the parentheses. We'll use the caret to go up into the exponent. I always suggest putting the exponent in parentheses, 4 times 5, close the parentheses. If you have to scroll out of the exponent, depending on the type of calculator you have, minus 1, close the parentheses, divided by, and here we have our extra parentheses, 0.09 divided by 4, close the parentheses, and finally we get to hit enter. And so the amount that's going to be in this account after the 5 years is going to be $49.82.30. $49.82.30. Now, kind of as an interesting aside, the problem didn't ask about this, but we put $200 in every quarter, so 4 times a year, for 5 years. How much money did we put into this account? If you multiply that out, you'll find out we put $4,000 into the account. That's how much went in, but that's how much we actually have, the $49.82. So we earned $982 in interest in 5 years. Not too bad. Let's take a look at this problem from a different angle, though. Often we know we need so much money at the end of a certain amount of time. Say we're buying an expensive piece of equipment, and we're going to put money into an account every year so that when the equipment fails, we can buy a replacement, and we continue to put money into an account so that when the equipment fails, we can buy a replacement, and we can keep going like this. So let's say I know I'm going to need $4,000 in 3 years. Maybe the expensive copy machine we have is going to go out in about 3 years. So we need to save up for this. So the question is how much should be deposited monthly in an account paying 14% interest. It's a very aggressive fund. It's going to get us a good return on our investment. Notice we're making regular payments into an investment. So we've got the future value amount is equal to the monthly payment, 2 parentheses, times 1 plus r over n to the nt minus 1 all over r over n. The $4,000 that we need that at the end in the future as our accumulated final amount. So that's going to be our A. 3 years, that's the time. It's deposited monthly, so N, our frequency of deposits, is 12 times a year. And the interest rate is 14%. So R equals 0.14. Plugging that in, A is 4,000 equals M. We don't know the monthly payment. Times 1 plus 0.14 over 12 to the 12 times 3 minus 1 all over the rate, 0.14 over 12. And again, we're going to remember the extra set of parentheses as we type it into our calculator. And we're going to have our calculator do this ugly fraction stuff because we're just going to have that stuff times n. Divide both sides by that stuff and we'll know what the monthly payment is. So back to our calculator, we've got 2 sets of parentheses. 1 plus 0.14 divided by 12. Close the first parentheses. Exponent key, in parentheses 12 times 3. Some calculators need the parentheses, some don't in the exponent. Some need you to scroll out of the exponent, some don't. Make sure you know how to use your calculator. Minus 1, close the parentheses. Divided by, these parentheses you do need, 0.14 divided by 12. Close your parentheses and hit enter. And we get 44.42. 44.42 M equals 4,000. So to solve for 4,000, or sorry, to solve for M, we divide by 44.42 to find what that monthly payment should be. So we're going to type in 4,000 divided by, and then again to make sure we get the accuracy of all the decimals, we're going to grab that previous answer. Second answer is going to grab that 44.4227995. Make sure it's exactly correct. The monthly payment is 90.04. $90.04 per month in this account paying 14% will give us $4,000 in 3 years. As an aside, I'm always interested in how much do I actually put in there. 90.04, 12 times a year for 3 years. And if I plug that into my calculator, we'll end up with 3241.44. So if I put 3241.44 in, I will have the 4,000 at the end of the 3 years because the rest is all earned in interest. So those are annuities. Annuities are regular payments into an account earning interest at the end of the period. And that last part of the definition sometimes throws students off, at the end of the period. Most accounts pay the interest at the end of the period. So you put the money in at the beginning and the interest is paid at the end. So I put the money in on the 1st of the month, I earn the interest on the 31st of the month. That's technically not always the case. There's these things called an annuity due, which is when we make regular payments into an account earning interest at the start of the period. And for these, the equation is going to be very similar with just a slight adjustment. A is equal to m times 1 plus r over n to the nt plus 1, because we get that extra payment because it came in at the start of the period, not the end, minus 1, all over r over n, but then we have to subtract off the monthly payment that hasn't been put in there yet because it happened at the same time. So the formula is a little different. We're not going to use this formula at all on the test. It does show up on a few homework problems, but the majority of the problems look at a regular annuity, payments made and interest paid at the end of the period. But for completeness, there it is. If it shows up on the homework, interest paid at the start of the period, you have to grab this formula. We're not going to spend any time on it, though, here today. Instead, we're going to go to the second half of our discussion. And the second half is, instead of earning interest for yourself, you're going to be paying interest on somebody else. These are called installment payments. That are made on loans. So if you're making payments on a loan, interest is being added, your payment is being subtracted. You see how that's similar to an annuity? In an annuity, you earn your payment and the interest. With the loan, the interest is added, the payment is subtracted, and hopefully you're going down towards 0 on your loans. So to kind of set this up, I'm going to tell you a story about two people. There's Mr. Cash, who saves up cash for everything, and Mr. Credit. My pen's not working. There it goes. And Mr. Credit, who puts everything on, you guessed it, credit. They want to buy a car. Worth A, some future value accumulated amount. Mr. Cash, actually let's call this A, so we'll organize it. Mr. Cash is going to pay a lump sum for the car, right? Well, that lump sum could be invested by the company over the period of a loan. So how much money is the company going to make? Well, it's a lump sum investment. And so we know A is equal to P times 1 plus R over N to the NT. The present value of the vehicle times the investment the car company is going to make by investing that lump sum. Lump sum payments from yesterday. Mr. Credit made payments. And so from the car company's view, they're going to invest the payment every month over time. So because they're investing monthly payments, this is essentially an annuity from the viewpoint of the car company. So they're going to have that M times 1, two parentheses, 1 plus R over N to the NT minus 1 all over R over N. The car company wants to have the same result at the end of the loan or the end of the lump sum. They don't care which is done. So the car company wants to make sure that they both pay the same at least in terms of how much is in the account at the end of the 5-year period of the loan, or whatever situation that is. And that is when the equations are equal. You notice that they're both equal to A. Well, if those A's are the same value, the same amount in the account, either investing a lump sum for 5 years or making payments for 5 years, we want the same amount in the account when the equations are equal. And so that gives us our installment payment formula. P, the present value of the car, times 1 plus R over N to the NT, is equal to, that's the lump sum, now the payments, M times 1 plus R over N to the NT minus 1, all over R over N. And just to clarify all of these definitions, all these variables, we've seen them all before, but P is the present value. You could think about it as the initial starting loan amount. R is the interest rate. N is the number of payments. Running out of space. I'm going to put that on the next line. I'll say T is time on this line. And as always, in years. N is the number of payments. Per year. M is the regular payment. Again, usually it's a monthly payment. And is that all the variables? Got R already, N already, T already. Yep, that's all of them. So this is our loan formula, basically setting the lump sum and the annuity equal to each other. Color in all the holes, right? Make it a pretty yellow formula. So let's see if we can use this formula to find out monthly payments on loans, find out kind of how it all works out. So number 2. We're going to find the monthly payment. For a $12,000 car on a 5-year loan at 3.8%. Okay? Well, we know the formula for the loans is P times 1 plus R over N to the NT equals M times 2 parentheses 1 plus R over N to the NT minus 1 all over R over N. And so we need to find out what we can plug into here. $12,000 car, that's the initial starting value for the loan. It's the present value of the loan. That's our P. It's a monthly payment, so the number of payments a year is 12. 5-year loan, that's the time. And the interest rate 3.8 is 0.038. And so we're ready to plug everything in, and we should only be missing the answer to our question, the monthly payment. So P is 12,000 times 1 plus R, 0.038 over N, which is 12, to the N, 12, times T, which is 5, equals the monthly payment times 2 parentheses 1 plus r, which is 0.038 over 12 to the nt, 12 times 5 minus 1 all over r over n, which is 0.038 over 12. There's going to be two parts to this. We have to type into the calculator separately to find out our final solution. So let's do the left side first in our calculator. Make sure the exponent is in that extra set of parentheses. 12,000 times 1 plus 0.038 divided by 12, close the parentheses, to the, open the parentheses, 12 times 5 power. Hit enter. Now the first number I'm going to type in my calculator, I'm going to copy down as accurately as possible. The reason for this is we're not going to have that previous answer feature because we're going to do another calculation and we're going to lose this number. So 14,506 .63963 63963 is equal to, now we're going to type this other part into the calculator and multiply it by m. Remember, we need the extra parentheses around the denominator and the extra parentheses around the exponent. Move the calculator to the other side so we can see. 2 parentheses, 1 plus 0.038 divided by 12. Whoops. Delete. Close the parentheses, raised to the parentheses 12 times 5. Close the parentheses, get out of the exponent, minus 1. Close the parentheses, divided by, the denominator needs an extra parentheses, 0.038, divided by 12. Close the parentheses, and hit enter. 65.96. 65.96 m. And so to solve this, I just have to divide both sides by that 65.96 to find what the monthly payment is going to be. So I'm going to move the calculator back over. So that 14,506.63963 divided by, I can grab the previous answer here because it's sitting right above. We can only grab the answer right above. Second answer, and hit enter. And the monthly payment for this car is going to be $219.92. $219.92 rounded to the nearest penny. They might round up or they might round down, whatever's closest. And the way they fix for the rounding is your very last payment on the loan is usually different by a few cents to make up for the rounding. Basically, it's your payoff amount is different by a few cents. But for all intents and purposes, the monthly payment for this car is $219.92. Here's an interesting question, though, that we can look at. Number 3. A lottery pays $200 per month. Oh, I'm sorry, that's not very exciting. Let's make it exciting. $2,000 per month. For 10 years. You can choose to receive a lump sum now Do you want to receive $2,000 per month for 10 years? For some reason my M's aren't showing up. $2,000 a month for 10 years, or do you want to receive a lump sum right now? Well, that depends on the interest rate. If the interest rate is 9%, what will the lump sum be? Lump sum now, $2,000 a month for 10 years. Depends. What should that lump sum be? We're going to look at this problem in kind of a similar way, and then we'll kind of do a variation of it on the end. But we're looking at regular payments per month for 10 years. That regular payment formula is P times 1 plus R over N to the NT equals the regular payment times 2 parentheses 1 plus R over N to the NT minus 1 all over the rate divided by N. What we are looking for is what that lump sum is going to be right now. How much money is this regular payment worth now, today? That is the present value that we're looking for. So we've got this $2,000 per month. That's the monthly payment, the regular payment. 10 years, that's the amount of time we're going to be receiving it. It is per month, so the number of payments per year is 12. And it's at 9%, so the rate is 0.09. So when we plug all of this into our formula, we'll find out what this lump sum payment is going to be worth. P times 1 plus R, which is 0.09, over N, which is 12, to the NT, 12 times, what was it, 10 years? Equals the monthly payment of $2,000. Times 1 plus the rate, which is 0.09, divided by the 12 payments, to the 12 times 10 minus 1, all over R over N, which is 0.09, divided by 12. So in this case, we're solving for our P. Again, we're going to have to put both sides into the calculator. Doesn't really matter which side we do first. We're just going to have to make sure whatever we do first, we type in our answer very exactly. So we've got parentheses 1 plus 0.09 divided by 12 times, getting ahead of myself, exponent, and then the exponent in parentheses 12 times 10. Hit enter. 2.4513. 2.4513, 57078, 57078 P is equal to, plugging the other side into the calculator. Let's see if I can, whoops, come on, there it goes. Move it over so we can see what we're dealing with. So we've got 2,000 times, 2 parentheses, 1 plus 0.09 divided by 12, close the parentheses, to the, in parentheses, 12 times 10, close the parentheses, getting out of the exponent, minus 1, close the parentheses, divided by, and again the denominator always in parentheses, 0.09 divided by 12, close those parentheses and hit equals. We have 387,028. 387,028. Let me get that circle out of the way. Point, let's get some cents in here, 55. So to solve for the P, We just have to divide by that 2.451357078 on both sides. Probably a little more than we had to do to get accurate to the penny, but that's okay. So we're going to take that previous answer, second answer, and we're going to divide by the 2.451357078. And that lump sum is 157,883. 157,883.79. So, here's a question though, just kind of as an aside to play with this a little bit more. What if we took that lump sum and instead of spending it, what if we invested it for the 10 years? What if I took the 157,883.79 and invested it for 10 years? How much money would I have? Well, that's 1 plus 0.09 divided by 12 to the 12 times 10. It's a lump sum payment. And we can just put this right into our calculator. Take that previous answer times 1 plus 0.09 divided by 12 to the, in the parentheses, 12 times 10, close the parentheses and hit enter. 387,029.54. 387,029.54. So his total winnings is $387,029.54 if he were to invest that lump sum instead of taking it as $2,000 monthly payments. Interestingly enough, if we were to take those monthly payments and invest them over the time, not spending those $2,000 a month, we would also have $387,029.54. So that's our introduction to annuities and installment payments. 2 new formulas for you to work with on the homework assignment tonight. And come to class with questions, and we'll see if we can make you a millionaire using this stuff.